This is a distributed systems course. In this lecture that we will see what is vector clock. And before that, we will revise the Lamport clock and why we need a vector clock. First, Lamport clock, we already seen what is Lamport clock. It uses a counter to represent a time, and we can send and receive the message along with the counter so that we can identify the message. So we can use it for ordering, but the event happened before B, so we can say that A happened before B, and it's called partial order. This partial order happens before relationship can be maintained here, but we cannot say the counter alone in Lamport clock alone that whether the two events are concurrent, whether the two events that happened are concurrent or casual. Casual means whether it is happened before or whether it is a concurrent. For example, here, even though we have a 5 and 6, this, even though it is lesser than the 6 for the same message, this event didn't cause this event. So let's say it's a C, it's a D. C didn't cause D. Also, C, we do not know whether it is a concurrent or not. So how do we define whether it is concurrent or it is caused this one? So we can use a vector clock. So you will see here vector clock. It's the same example. So we have to change the algorithm little bit. Why? Instead of single, we are going to maintain array of vector. So it's 5 machines. We will maintain 5 counter. So each event occur on local machine, we will increment that particular counter. Event occur to send message. Here we will increment the message and send the counter, timestamp along with this message. On receiving the message, let's say here current clock of J and received clock of J. We will get the maximum of this vector counter. And finally, we will also update one more thing here. TFI equal to TFI plus, which means we are updating the local counter, also the counter that is send the message. So we have vector counter. We will receive and send message across all those machines at the same time that we will update the counter as we did it with the Lamport clock. Here we will see again. Let's say this machine has a counter 0, 0, 0. 5, 0. So initially everything is the vector. Vector is this one, initial counter is. So the client sent the message. We will see this one. Now the client sends a message. This one is here. Now it receives the message, and now it increment for the event. It's counter S1. Then again it sends with the message here. Also it persists those message with vector and message. Vector command is vector is a counter, array of counter. Now it sends a message. Here it will receive the message. It does the same as we did in lumber clock. It does the same. So it will increment the received one. Also it will increment the current one. Then it sends a message to this one. It will increment this one and send it. When it receives, it will update all the relevant vector counter. And here it is 1. By the time it is sent, it will become 2. When it receives, it will get the max of it and update it. At the same time, it will increment the current one. Same for other things also. So it will send the message incremented. It will receive 2, then 3, then 0, 0, 0. It will increment the current one. When it sends, it will increment the current one. Now 3, 0, 0, 2, this one is 3. Since it receives and updates it, when it sends, it will increment the 2, sends it. When it receives, get the max of it and update it. Also it increment the current counter. Now we have this is how the total vector clock is updated whenever messages are sent across those messages. So it updates its own counter. Also it updates the machine that send it with the max of it. Now this one is less than this one. We compare all the vector counter. This one is less than this one. We compare all the vector counter. So this happened before, this happened, this one before. We can say this one happened before. We can say whether this one happened before or concurrent. How this one, since when we compare this, we have a 2, so less than 3. We have 3, which is greater than 0. So the ordering is not comparable. So these are concurrent. We can say the same for this one. The ordering is not comparable. So we can say these are concurrent. But here we can say this one is caused by this one. So this one is lesser than this one. We can say this is casual. 3, 0, 0, 3, 1, 0, 0. So this is how the casuality and concurrent update is maintained using vector clock in a distributed systems, whether it is a database or cache. So this is a simple example of we seen the Lampert clock and vector clock. So what Lampert clock can do and what vector clock can do. Vector clock can maintain. Vector clock can say that whatever that happened between the machines for the message, whether it is a concurrent or casual. Casual means whether it is happened before relationship is maintained. So these things are casual. These things are casual, but these things are concurrent. So we can come to conclusion by comparing this vector counter. So this is vector clock.